Okay, let's go back to our data. And just realized that I've lost my the graph that I made earlier. Okay, this is very I have to share the whole screen again. Bear with me, I'm wrestling with. Okay, now I can see my whole screen. And okay, so what does the grouped box plot tell us, right? So that's the information. And by making a grouped box plot or side-by-side box plot, we are already starting to answer some interesting questions about what influences. Well, first of all, what are the differences between different regions at the lower tier local authority level about the coronavirus, right? And first of all, there's this one local region has one local authority has exceptionally high value of virus. Okay, not sure if that's real, but we can see some outliers here. Identify those outliers later if you want to. If you just want to figure out what's going on in those places. But let's add in make it a grouped box plot. In the most okay. Now we have a group box plot. We can see that, first of all, which region has more than the other regions. And we can also see which regions has more variation than the other regions. Again, at the lower tier local authority level. London seems to have overall a higher London like local authorities in London have higher numbers of cases overall, but the variation also seems to be smaller. And Northeast have a higher variation. Yorkshire has a huge variation. West Midlands has some outliers, as we can call it. So is Yorkshire, right? I'll quickly close the door because my cat just walked in. So give me a second. I think he's also interested in the making charts on Excel. But as you can see, and of course, as a cat now he wants to go out. As you can see, that this gives us interesting information about the coronavirus at the lower tier authority level across different regions. Okay? And although it doesn't really provide us some conclusions about statistical significance, but this is a way of visualizing the data and shows regional differences in that regard. And we can see Southwest has the lowest, seems to have the lowest. East Midlands seems to have the lowest level of cases. So this is the idea of exploratory data analysis. which is to eyeball the data and to visualize the data before you conduct any statistical analysis or testing on the data, right? You'll be spotting for outliers, spotting for mistakes, spotting for symmetrical, the shape of the distribution, whether it's symmetrical or not, which will be important for the next steps of the analysis, okay? Okay, so we have made a grouped box plot in Excel. The final step is quantitative relation, where both independent variable and the dependent variable are quantitative variables. So the method that people usually use to explore this kind of relationship is to make a scatter plot. For example, if we say a study explored driver's age and the maximum distance at which they can see the signs. So they found 30 drivers of 18 to 82 years old, and they measured the maximum distance at which they can read a newly designed sign. And so to the left we have data. Each driver has a cooped, what I say, like a cooped pair of values. Cooped means that they're basically paired, and of age and distance. Driver 2, 32, 410, driver 3, 55, 420, etc., etc. So this pair of values can be further mapped onto a coordinate of x and y axis, two-dimensional coordinate. So for driver 1, each observation is now turned into a dot in the scatter plot. The driver 1 with an age of 18, the age is now mapped onto the x-axis, and the longest, the sign legibility distance is now mapped onto y-axis, and the dot is placed according to these values, a pair of values. And now we can also do that for driver 2, right? And we can finish that. This is the finished one, scatter plot for all 30 drivers. So again, we have 30 dots because we have 30 observations. And this gives us an idea about the relationship between these two independent variables. And it seems that when the driver gets older, as they get older, they see closer, right? So, and to test whether there is a linear relation, you will have to use a correlation or regression to actually test this seemingly linear relationship. But this gives us an idea of the direction and the extent of the relationship. Right? So let's try to make a scatter plot in Excel using the data that we provided, and then we call it a day. Okay, so go into the Excel screen again. I'm going to the desktop. Okay, now see the Excel file. Delete this. Okay. Let's say that we're interested in what really explains what makes some lower tier of some local authority or counties or wards more, give them a higher likelihood to get coronavirus cases. And So we have the cumulative lab confirmed cases, and we have population of these local authorities, right? So this makes me think that it is possible that the higher the population is, the higher number of population, then the higher number of cases, right? So that can be we can try to depict that relationship using a scatter plot. So what we can do is basically select these two, and we do go insert, and there's this little chart called scatter. Okay? So we have to select the first one, just simple scatter plot, and there we have it, right? And it seems like the x-axis from 0 to 3,500 is the number of cumulative lab confirmed cases, number of cases. And the population is on the y-axis. Now what we want to do usually is that we want to put the independent variable on the x-axis. Okay? Let's make this bigger. So that's the scatter plot, right? Each represents the local authority, y-axis is the population, x-axis is the number of cases. But we want to switch row and column, and there's a option here for Mac. I think you can also select data, and then you can switch row column there. I think that applies to Windows version as well. Okay, so you have switch row and column, and okay, nothing happened. Let me see. Number of data series per chart is 255. Okay, I think I still have to figure out how to do that. Okay, x values. Okay, you have to change the x values, y values manually. So you want to G to be the x value, F to be the y value, and then OK. No, that's not what I hoped for. Wait, select data. I don't think that's what I wanted. X value population, y values. Huh, for some reason this is not working very well because of the population. Let me just do that again. Lines. I'm not going to change the axis. So this seems to suggest that there seems to be some kind of linear relationship going on between these two, right? Which makes a lot of sense. If you have higher level of population, you have higher level of cases. If the infection rate is the same, they're confounded basically, because infection rate, the number of cases equals the population times the infection rate. So what we want to do is to control for population. Okay, so to do that, we can calculate something called case per 100,000 people in the population. So this is done by dividing the lab cases, number of cases, by the population of that local authority. So you can see that on the formula, it's F2 divided by G2. because that number is too small, I time it by 100,000, right? So now we have case per 100,000, which you can see now this is affected less by the population, right? So for population of 9,000, you still have 174, right? So this estimation has controlled the case per 100,000 is a better measure of infection, controlling for the population of the local authority. The other way, another thing is, let's say that I'm interested in how local population density affects the infection. Okay, so the idea is that the more dense the area is, the more likely people are infected. And density, again, I get the density data from the data provided by the National Statistics. I think somebody asked a question, or nope. Okay, so now I'm interested in whether density is associated with this population controlled infection, right? So let me create a chart, about a scatter plot that describes this. Okay. This time on the x-axis we have density. On the y-axis we have case per 100,000. Again, there is a outlier there that has only very low density, very high number of cases per 100,000. Let's look at what that area is, right? Because I'm curious. So it's at 0.860. We could try to label it, add data label from the name, but I'm not going to do that. I'm just going to go to 860 to see which one it is. It's 0.860. Okay. I think that's the one. Okay. Barrel and furnace. Okay. So, yeah. I think I've heard about it in the news that there was like town, a remote area in Cumbria somewhere. Cumbria. There's a unusually high infection rate. Again, this outlier tells us that there's an outlier, there must be something going on there. And overall, this trend is this seems to be, okay, this is the density, and this is the infection rate on the y-axis. Now, it doesn't seem to me the linear relationship is so clear, right? But we don't know that because what we could do is to add trend line. Okay, so you can right click on any of the data dot, any of the dot in the scatter plot, and then you can add trend line. Okay, add trend line, and you have some options there: exponential, linear, logarithmic, polynomial, power, moving average. What this trend line does is a regression line that depicts the linear relationship between the two variables, the extent. Right? by extent, I mean that it's going to stay linear, but the how steep or shallow this line is, right, depicts how much a change in population density changes the rate of infection. Does that make sense? So what it does is it shows that each unit of change, I'm losing my plot. Okay. So each unit of change of the x-axis will lead to this unit of change on the y-axis, on the dependent variable. Now, this regression line, what it did, it's trying to fit in to minimize the distance of each dot to this line. Okay. So if you measure the distance, so this line goes through these dots, and each of these data points, the distance to this line, to this trend line, can be is estimated in a way that it minimizes the distance of the sum of distance of all these dots to the trend line. Okay, and we are forcing it to be linear, but we can try other kinds of options, such as it might be the case that they have exponential relationship instead of a linear relationship, right? They might also have a logarithmic relationship or polynomial relationship that might fit it better. Okay. So if we just delete the previous trend line and now add a trend line that is polynomial, this might actually fit it better. Right? Right? So there's an increase as the density increases to a certain point, the infection rate goes up. But then after that point, as the density goes up, it is possible that the infection rate goes down. Okay, probably because people are more aware of the density of the local authority and they don't go out as much. Okay? So, but again, this doesn't really provide us with how well these trend lines fit. It provides us with the best fitting trend lines in different shapes, but doesn't really describe how good or bad these lines fit. Doesn't provide goodness of fit, right? So in order to evaluate which relationship fits the data the best, we probably need some more information about how well these trend lines fit our data. Okay? But it's very important to add a trend line, right? Otherwise, the whole scatter plot is kind of chaotic. So adding a line there gives us some kind of assurance that there is a linear relationship, no matter how good that relationship is, or how strong or how weak it is. It shows us some kind of trend, right? So in this case, it seems that overall, as local population density increases, case per 100,000 seems to increase. But again, there's outliers that might have affected this, right? And in this case, what's going on in the outlier is very interesting. And to figure out what happened there that causes this kind of unusually high infection rate is actually quite important. And that's the thing about outliers. You can have outliers for that has very little value that you just delete, but sometimes outliers can be very interesting, that provides you with cues to interesting findings. Okay, we'll talk more about scatterplot in the next lecture, but this is just a quick summary of how do you do exploratory analysis before after you get the data and before you do any statistical testing, right? So again, the purpose of exploratory data analysis is just to visualize the data and give you a chance to spot the outliers, give you an opportunity to evaluate the distribution of these variables, so you can decide whether certain statistical methods, testing methods, are more suitable than the others, because different statistical testing have different assumptions about the distribution of variables, and sometimes when those assumptions are violated, the test becomes less reliable. So it's important to check the distribution of variables. So in the CC relationship, you can use two-way table. You can use basically you extract information of conditional percentages to depict this relationship. For CQ relationship, you can use side-by-side box plots, or you can use just descriptive statistics. There are more advanced graphing options available in in R, for example. They can allow you to do so-called violin plot, or basically colored histogram. So two histograms side by side or overlapped, each color indicates a different group membership, right? But a categorical quantitative relationship, CQ relationship, is all about how do you categorize, how do you map the quantitative variables distribution onto different categories. Again, QC is not covered in the module, but for QQ, the most common method is scatter plot. Okay? And to test the relations, which we will not address, in the next 3 lectures, we will not focus on this, but this is for the future, that in order to test whether these relations that we explored are actually significant, statistically significant, we have different methods. For CC relationship, we use chi-square test as one of the tests. For CQ relationship, we use t-test or analysis of variance. And for quantitative categorical relationship, it's not covered. And for QQ relationships, we use correlation or regression. Okay? So again, these are for lecture 5 or 6 and onward. So that's it for the next lecture. I think that we already seems like we still have to figure out what to do, and it seems like we're not going to have it on Tuesday. We're trying to figure out whether to have it on Thursday morning, or we just push everything back for one extra lecture. Okay. So in the next lecture, we will switch on to probability. And that's the important step before we we go to any statistical testing, is to understand the idea of probability. And the lecture after that, we will talk about sampling. Okay. So remember, what we're trying to do is to estimate the population from a sample, a subset of the population. And to understand how that subsetting affects how the subsetting process works, and how the sampling statistics changes in relation to the population parameters, is key to understanding statistics testing. Okay, so this is it for this week's lecture, and I'm going to pause recording, and if you have any questions, you can still let me know. Otherwise, I'll have a good weekend. It's a long weekend, and I'll see you next week sometime.